Welcome to Section 7, Lesson 9. So far in this section we have built polynomial vocabulary: addition, subtraction, multiplication, division, the remainder and factor theorems, and graph sketching. Today we use the factor theorem and synthetic division together to find rational roots of polynomials with integer coefficients. The rational root theorem provides a finite list of candidate rational roots, narrowing what would otherwise be an infinite search to a manageable set. Combined with synthetic division for testing each candidate, the rational root theorem gives a systematic algorithm for finding all rational roots of any integer coefficient polynomial. Today we lock in the candidate list construction, the testing workflow, and the polynomial reduction step that follows each successful root finding. First idea on the board, the rational root theorem statement. If a polynomial p of x with integer coefficients has a rational root expressed in lowest terms as p over q, then p must divide the constant term of p and q must divide the leading coefficient of p. The theorem narrows the search for rational roots from the infinite set of all rational numbers to a finite set determined by the divisor structure of two specific integer coefficients. The candidate list is built as plus or minus the ratio of any factor of the constant term to any factor of the leading coefficient. Second idea, building the candidate list. To construct a rational root candidate list for a polynomial with integer coefficients, identify all positive integer factors of the constant term and call this set P. Identify all positive integer factors of the leading coefficient and call this set Q. The candidate list is plus or minus P over Q for every combination of P in the constant factor set and Q in the leading factor set. Duplicates are removed. For example, if both leading and constant are 6, the candidate list will have repeats like 1 over 1 and 3 over 3 that simplify to the same number. The final candidate list is finite, and every rational root must appear in it. Third idea, testing the candidates. Apply the factor theorem with synthetic division on each candidate from the list. Run synthetic division by x minus c for each c in the candidate list. If the remainder is 0, c is a rational root, and the quotient polynomial in the tableau is the polynomial divided by x minus c with degree 1 less. Repeat the testing on the reduced polynomial to find further roots. Stop when all candidates are tested or when the polynomial has been reduced to a quadratic, at which point use the quadratic formula or factoring directly. Today we drill the workflow on a worked example with multiple rational roots. The rational root theorem provides a finite list of candidate rational roots for any polynomial with integer coefficients. Combined with synthetic division for testing, the theorem gives a systematic algorithm for finding all rational roots of the polynomial. Theorem statement: for polynomial p of x with integer coefficients has a rational root p over q in lowest terms, then p divides the constant term of p and q divides the leading coefficient of p. Equivalently, the numerator must be a factor of the constant term and the denominator must be a factor of the leading coefficient. The two divisibility conditions narrow the search from all rational numbers to a finite candidate set. Candidate list construction. To build the candidate list, find all positive integer factors of the constant term, call this set the p-values. Find all positive integer factors of the leading coefficient, call this set the q-values. The candidate list contains plus and minus the ratio p over q for every pair, often written as plus or minus p over q for clarity. Reduce duplicates and simplify fractions. The final candidate list is the complete set of possible rational roots. Every rational root of p appears in this list, but not every entry of the list is necessarily a root. Testing each candidate. Apply the factor theorem via synthetic division on each candidate from the list. For candidate C, run synthetic division by x minus c. If the remainder is 0, c is a root and x minus c is a factor of p. The quotient polynomial in the tableau is p divided by x minus c with degree 1 less than p. If the remainder is non-zero, C is not a root and we move on to the next candidate. Reduce and repeat. After finding a root, work with the reduced quotient polynomial which has degree 1 less. The remaining rational roots of P are also roots of the quotient, so the candidate list and testing procedure can be reapplied to the quotient. Continue until the polynomial is reduced to a quadratic, at which point the quadratic formula or direct factoring finds the remaining two roots, which may be rational, irrational, or complex. The combined workflow finds all rational roots systematically. Here is the first worked example. Find all rational roots of p of x equals 2x cubed minus 3x squared minus 8x minus 3. Use the rational root theorem to build the candidate list and synthetic division to test each candidate. Step 1. Identify constant and leading coefficient. Constant term is -3, leading coefficient is 2. For the candidate list, we need factors of 3 for the numerator and factors of 2 for the denominator. Step 2. Build candidate list. Factors of 3 are 1 and 3. Factors of 2 are 1 and 2. Candidate P over Q values are 1 over 1, 1 over 2, 3 over 1, 3 over 2. With plus or minus signs, the candidate list is plus and minus 1, plus and minus 1 half, plus and minus 3, plus and minus 3 halves. 8 candidates total to test. Test C equals 1. Synthetic divide P by x minus 1. Coefficients 2, -3, -8, -3. Bring down 2. Multiply 2 times 1 equals 2. Add -3 plus 2 equals -1. Multiply -1 times 1 equals -1. Add is -8 plus -1 equals -9. Multiply -9 times 1 equals -9. Add -3 plus -9 equals -12. Remainder is -12, not 0. So C equals 1 is not a root. Test C equals -1. Synthetic divide by x plus 1. Bring down 2. Multiply 2 times -1 equals -2. Add -3 plus -2 equals -5. Multiply -5 times -1 equals 5. Add -8 plus 5 equals -3. Multiply -3 times -1 equals 3. Add -3 plus 3 equals 0. Remainder is 0. So C equals -1 is a root. Step 5. Reduce using the found root. The quotient from the table has coefficients 2, -5, -3, giving the quotient polynomial 2x squared minus 5x minus 3. Factor this quadratic. 2x squared minus 5x minus 3 factors as the quantity 2x plus 1 times the quantity x minus 3. Roots of the quadratic are x equals -1/2 from 2x plus 1 and x equals 3 from x minus 3. Step 6. Compile final root list. The full factorization of p of x is the quantity x plus 1 times the quantity 2x plus 1 times the quantity x minus 3. The roots are -1, -1/2, and 3. All 3 are in the original candidate list, confirming the rational root theorem narrowed the search correctly. So the rational roots of P are -1, -1/2, and 3. The big lesson from this example is that the rational root theorem candidate list is finite, the testing via synthetic division is mechanical, and the combined workflow finds all rational roots systematically. The factor theorem reduces a high-degree polynomial to a quadratic in a few steps. Here is a second worked example. Find all rational roots of p of x equal x cubed plus 2x squared minus 5x minus 6. Apply the rational root theorem and synthetic division systematically. Constant term is -6, leading coefficient is 1. Factors of 6 are 1, 2, 3, 6. Factors of 1 are just 1. Candidates are plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. 8 candidates total. Step 2. Test C equals 1. Synthetic divide. Coefficients 1, 2, -5, -6. Bring down 1. Multiply by 1, 1. Add 2 plus 1 equals 3. Multiply 3. Add -5 plus 3 equals -2. Multiply -2. Added -6 plus -2 equals -8. Remainder -8, not 0, not a root. test C equals -1, synthetic divide, bring down 1, multiply by -1, -1, add 2 plus -1 equals 1, multiply -1, add -5 plus -1 equals -6, multiply 6. Add -6 plus 6 equals 0, remainder 0, C equals -1 isa root. Reduce. The quotient is x squared plus x minus 6. Factor x squared plus x minus 6 factors as the quantity x plus 3 times the quantity x minus 2. Roots of the quadratic are x equals -3 and x equals 2. Step 5. Compile final root list. The factorization of p is the quantity x plus 1 times the quantity x plus 3 times the quantity x minus 2. The roots are -1, -3, and 2. All three rational, all three appear in the original candidate list. Step 6. Verify by multiplication. Multiply x plus 1 times x plus 3 times x minus 2. Start with x plus 1 times x plus 3, x squared plus 4x plus 3. Multiply by x minus 2x cubed minus x squared plus 4x squared minus 8x plus 3x minus 6, which collapses to x cubed plus 2x squared minus 5x minus 6. Matches the original polynomial. Verification complete. So the rational roots are -1, -3, and 2. The big lesson from this example is the systematic nature of the rational root algorithm. Build the candidate list from the constant and leading coefficient. Test each candidate via synthetic division. On hits, reduce the polynomial and continue. The algorithm terminates after at most degree many synthetic divisions and finds all rational roots reliably. 3 mistakes that catch every algebra student during their first weeks of rational root theorem work. Each one is fixable with a small explicit habit applied on every problem from now on consistently. First mistake, forgetting that Q must be a factor of the leading coefficient and writing the candidate list as just plus and minus the factors of the constant. A student looks at 2x cubed minus 3x squared minus 8x minus 3, sees constant -3, and writes the candidates as plus and -1 and plus and -3, missing the fractional candidates like plus and -1/2 and plus and -3/2 that come from leading coefficient 2. The fix is to always identify both the constant factors for p and the leading coefficient factors for q, and to enumerate every plus or minus p over q combination explicitly. The fractional candidates are real candidates and must be tested. Second mistake, skipping negative candidates and testing only the positive ones. A student tests 1, 2, 3 but forgets to test -1, -2, -3. The rational root theorem includes plus and minus signs on every p over q candidate, and many polynomials have negative rational roots. The fix is to always include both signs in the candidate list and to test both signs for every p over q combination. Negative candidates are equally important and equally likely to hit. Third mistake, stopping the algorithm after finding the first root and assuming the polynomial has only one rational root. A student finds c equals 2 as a root, moves on to factor the remaining quadratic, and ends up with 2 non-rational roots when actually a third rational root was waiting in the candidate list. The fix is to always continue testing remaining candidates on the reduced quotient polynomial after finding each root. The algorithm terminates only when all candidates are exhausted on the current polynomial, not when one root is found. The rational root theorem shows up across polynomial factoring, computer algebra systems, cryptography, and numerical analysis continuously. 4 broad sectors below where every working professional applies the theorem or its analogues routinely. In algebraic polynomial factoring, the rational root theorem is the workhorse method for breaking down a high-degree integer coefficient polynomial into linear and quadratic factors. After extracting all rational roots via the theorem, the remaining quadratic or higher polynomial is factored by other methods like the quadratic formula or special product identities. The algorithm appears in every algebra and pre-calculus textbook and is essential preparation for calculus and beyond. In computer algebra systems like SIMPy and Python, Mathematica, Maple, and Maxima, the rational root theorem is implemented as a fundamental subroutine for symbolic polynomial factorization. Modern computer algebra software uses optimized variants of the theorem that handle large coefficients efficiently and combine the candidate testing with other root finding heuristics for speed. The mathematical foundation is exactly the theorem from this lesson, scaled to industrial polynomial computation. In cryptography over finite fields, polynomial factorization plays a central role in many cryptographic constructions, including elliptic curve cryptography, lattice-based cryptography, and post-quantum cryptography. The rational root theorem has analogues in finite field polynomial settings, and the underlying algorithmic ideas of candidate enumeration and divisibility testing extend directly. Modern cryptographic software uses these polynomial algorithms continuously for key generation and ciphertext processing. In numerical analysis for polynomial root finding, the rational root theorem is used as a preprocessing step to locate rational roots exactly, before iterative numerical methods are applied to find irrational and complex roots. The exact rational roots provide accurate factorization for the polynomial reduction step, and the iterative methods then handle the remaining quadratic or higher residual factor. Combined exact and numeric approaches are the standard in scientific computing libraries. 3 things to take with you from this lesson today. The rational root theorem combined with synthetic division is the standard algorithm for finding rational roots of integer, coefficient polynomials. Today's workflow is the foundation of polynomial factorization in algebra and is used continuously in computer algebra systems and numerical analysis. First, the rational root theorem says that every rational root p over q of an integer coefficient polynomial in lowest terms has p dividing the constant term and q dividing the leading coefficient. The theorem narrows the candidate set from all rational numbers to a finite set determined by the divisor structure of 2 specific coefficients. Memorize the statement and apply it on every integer coefficient polynomial root finding problem. Second, to build the candidate list, enumerate the positive integer factors of the constant term as p-values, the positive integer factors of the leading coefficient as q-values, and form plus and minus p over q for every pair. Reduce duplicates and simplify. The candidate list is finite and contains every possible rational root. Test every candidate including both signs, skipping signs misses valid roots. Test each candidate via synthetic division by x minus c. 0 remainder means c is a root and x minus c is a factor. The quotient in the tableau is the polynomial divided by x minus c with degree 1 less. Continue testing remaining candidates on the quotient until all candidates are exhausted or the polynomial is reduced to a quadratic. The combined workflow finds all rational roots systematically and reliably. Coming up next, the lesson called Finding All Roots, which extends today's rational root algorithm to also handle the irrational and complex roots that may remain after the rational ones are extracted. The lesson teaches the full root finding workflow combining the rational root theorem with the quadratic formula and complex number algebra.